time. Oh, you're still recording. Well, because Alex appears to be there, but perhaps he's just gone more advanced, and we've got like an inflatable Alex there, and he's actually using the camera there. Yeah, you never check out what these things.
Well, no, the whole thing was that because there was enough people in the class asking for input for the videos, I'm just going to keep recording for the rest of the semester, essentially.
Yeah.
That sounds good. Now you can do the binge all of Seth's lectures right before binge. That would take quite a while considering each one's a minute.
An hour and
Well,
12
yeah,
Each one's a minute and 15 minutes, according to Alex.
Yeah.
Right.
Well, that's why I mean, that's how long it was when I skimmed through it. So they're on YouTube, you see, and YouTube has a speed up function. So you can watch it like 2
You
times.
can watch
They're all done in like 30 minutes.
That's probably way better.
Yeah.
Everybody
Yeah.
can watch Seth talking at double speed.
Yeah.
Sounds like a chipmunk.
Sure. That sounds quite useful. And actually, you know, if I applied that here and just talked twice as fast, I could finish the whole thing in like 30-some minutes.
I have 30 minutes.
Okay, so here's where the course calendar looks. I wanted to bring this up here just because the midterm is coming up closer than it is in certain other classes. It's advanced about a week in this class before the center of the semester in an effort to not clump all the midterms at the same time. So that's why it's a little bit early. Okay, so the October 1st week is when we have it. We're up in this week right here, and so we've got another midterm free week before we get there. But I want to talk a little bit about what goes on in the midterm today, demystify it a bit and let you prepare for it and whatnot. And then project 2 will be due sometime soon. It could be like the end of that week or something like that. I think it has a due date on it. There, that date. So right after that week. So that's the week to do it, and then it's due on Monday, so it's got to be done after that week's done. Okay, so that's where the calendar's going. Now we're just a little behind the schedule as stated here because we were talking about process management still on the first day of this week here. That should be system calls and data structures. So the effect on the schedule will probably be that the device driver demo gets pushed to the answers given on Thursday day. The answers don't take the whole period. I schedule them for a whole period because a lot of times the schedule is slipped by the time we get there, and that gives a chance to rescue it. So that's the plan there. So content for the midterm. Kind of test update. So C, we did C in project 1, and we didn't do that in lab 3 this time. This is different than the semester I wrote that stuff. So ignore that part right there. Anyway, so project 1 was heavily on C, and C had pointers. I'll actually probably give you a lab to practice this stuff later, which would be like lab 4. That probably should be what is sub lab 3 up there. Anyway, pointers and function pointers and struct and memory, so stuff that project 1 did. So if you understand project 1 now, it shouldn't be that big a deal. Usually I've given a test question that involves pointers in a structure, go figure, and you have to use them from inside the structure, either defining the structure or using the functions inside the structure and calling them, basically doing the other side of things. Anyway, so something like that. Have to understand these ones. And of course you have to know general C stuff like if statements and variables and whatnot. The kind of thing everybody started out knowing. Okay, and there's no test questions like specifically on those really, but
You just have to know how to use them.
yeah. Okay, kernel programming. So that's more a project 2 kind of focus. This project 2, the one I'll talk about in a minute. Project 2 covers making a file in /proc, and it follows out of the keyboard light blinking example. And /proc, how to use it, read and write functions in proc, and programming in kernel space. Now, you might not have finished project 2 by the time it's there. I'm hoping that you work on project 2, but if you have bugs and whatnot, then sometimes it takes a while to work out. But kind of generally understand how do you get a kernel module up and going and put it in the kernel and that sort of stuff. I have the wrong background. That's the one I want. Okay, and then programming on Unix platforms. So we've been talking a lot about processes and using processes. In lab 3, you get to go practice with catching signals. And so I should have kind of a general understanding how these things work, what processes are, and how to use standard library functions with processes. So that's on there, and then process management, kind of in general. Why would you want a short time slice versus a long time slice? And so this doesn't really have a project that it follows from, more general concepts. This follows under chapters 3 and 4. I won't have a strictly book question there, but the book goes into more detail and different detail than we did in the lecture. We talked a little bit more about process management from a using the operating system perspective, and the book talks about a little bit more in an internal, inside the operating system kind of perspective. And so I definitely recommend reading it because it's more complementary than it is the same thing I already said. So maybe more useful there. Okay, but I won't have a question that's strictly out of the book that wasn't talked about at all in lecture. I try to avoid that kind of thing. Okay, so let's test update. Questions? Test? And of course, there'll be questions on a test, but questions about the test. Okay, so that's a brief test overview, and can be considered a study guide. And so now you all know how to get an A on the test. Let's talk about fork bombs real quick. They were going to pop into the end of the lecture last time, but we just ran out of time. So everybody always likes fork bombs. They're a great topic. Okay.
I love the first line of your notes there.
Oh, yeah, yeah. So the way a fork bomb works, and we definitely won't practice these on a software. So there's a limit to how many processes you can have running on your system. And it's usually a pretty high number, but there is a limit. And so once you have that many processes, it jams things up so that you can't run any more processes. So there's a process table somewhere. It's got a fixed size, and it varies based on which operating system. You can actually query and get a limit. Usually fork bombs don't bother to check what the limit is. They just make sure they use it all up. So a fork bomb is actually really short and simple. So fork bomb.c. First of all, we have to call fork. So fork is in unit std. Okay. I'll just avoid name. It doesn't actually return anyway. Okay. When we call fork, we get two processes from fork. And so they usually we say something like this: PID T child PID equals fork, something like that, and get the child's process ID. Okay, so what we want to do is something like this. Okay, while in one, we'll fork. So when we do this, we actually don't need to say the process ID. So both the parent and the child will return to the top of this loop. At that point, each of them will call fork. So the first iteration, you got 1, then you got 2, you got 4, then 8, then 16, and so on.
And eventually we'll have more children than a colony of rabbits.
Yes, yes. This operates quite quickly, and then pretty soon we run out of space on the machine to start new processes. And I think I'll still be able to stop it with Control-C. So let's hope. There we go. Okay, so the computer's here. So you can't tell what I'm doing necessarily, but I've just pushed the button that normally starts a terminal, and no terminal was started. Let's go ahead and Control-C this, and I'll start another window. So I have two terminals. Okay, we'll go ahead and run it, and down here we'll type something very innocuous like ls. Isn't that interesting now? So bash, the shell here, needs to call fork in order to make a child process to run the program called ls. But it can't have a child process because the process table is full.
I love the last resource temporary unavailable.
Right. Now, we can actually have CD.
Are you sure?
Okay, we can't have CD. CD is a terminal command. It tells our terminal to do something as opposed to starting a program. But apparently, somehow, it depends on having a process ID space. Because the terminal just went away. And the fact is, I can't have it back. I figured you already had tab on the browser. I open this new tab on the browser and I try to go somewhere. it actually gives me, you can't probably see this in the projector, but it has a little frowning face right here. And that's because the web browser itself is multi-threaded, and not just multi-threaded, it actually operates each tab in its own process. That was one of the things that brought Google Chrome to early popularity compared to Firefox, for example. In Firefox, if you had some, banner ad that went crazy and took up an entire process's, just held up the CPU, the whole browser would come to a halt. With Chrome, it was just the tab. I think the other major browsers have followed their lead here, but it can't have a new process, so it can't have a new tab. We can probably change where we are on an existing tab, probably. Okay.
Try it and find out. It's not like we need that particular page anymore.
Okay. Sure, we'll go somewhere else.
Maybe.
Well, it probably has to start a few other things that start processes. I went to a complicated web page. How about a simple web page?
There you
A
go.
simple web page is fine. How about a less simple web page? Might not be okay. Oh, hey.
No, it froze.
No.
The computer will also be a little bit slow
Processing
because the entire process table is full of entries for this fork bomb that are busy calling fork as fast as they can. And they're getting an error value back from fork when they do it, but then they just try again. So the computer is sort of inundated with requests to start new processes.
I think it's not going to work
Yeah.
because it's not even attempting to load anymore.
In some ways, the multi-core processor is almost worse here because it can run fork even more frequently. Yeah.
So could you set up a signal handler in there to ignore Control-C and all that good stuff?
Yeah, you could. Yeah. Yeah, and if we do that, it'll make it a little bit harder to stop. You see, okay, I'm gonna make a stack of terminals here. Okay, I got a whole stack of them now. This is like a stack of Post-it notes. Okay, so now if I say something like PSAXU to show us the process table, no, we can't.
You also can't Control-C it.
No, I can't Control-C fork here, but eventually it will give up.
Yeah, it takes 5 tries before it does.
Okay, well, let's just switch to a different one. So I can do something like this. Exec uses up my terminal, but it manages to run a command. So I should be able to do something like this. Exec PSAXU, and then redirect it into a file. PS output. Okay. I'm hoping that it doesn't need a separate process or something for the redirect there.
I think it might.
Yeah, because you're actually going to create and write to a file.
Yeah,
so I
that could
would
be a
expect it to.
problem, actually. My cursor stopped blinking. Okay. So if I wanted to try it, one way that people try to, can you run clear? Okay.
I'm busy.
People like to do something like this. Exec kill all -9 a.out. Oh, that's spelled right. Luckily, it doesn't. You don't lose your terminal until you spell it right. Okay. So that terminal went away. It's done for.
And it kills the process.
Hey, I got it. Cool. Okay. So you can do that. Now, with each of the children, it's possible to name them differently than a.out and have a variety of names, in which case the kill all doesn't necessarily work.
Oh,
Let's see if I got
no.
anything in my PS output.
No, you didn't make
Wait a minute, what? Okay.
Uh-oh.
So we did something here that might have actually caused a little bit of a problem. So here's what's going on. Kill all -9 is killing processes named a.out. It happens to have killed the one that was associated with that terminal up there. That was my handle to the entire tree there where I could hit Control-C and take them out. Now, it's busy killing a.outs, and there's one kill all. However, the entire rest of the process table is filled with little, fork bomblets, which are busy trying to start more. So we've got like 1 versus however big the table is.
It's a single dude with a machine gun versus a zombie outbreak, and the zombies are multiplying faster than his bullets.
Okay, so what we need to do, we need to know something here that's maybe hard to know actually, at least for this machine. And that's what is the stop signal. Because there's a whole table of signals that we could potentially use. And one of them stops processes, leaving them in the table. So now here's the issue though. I don't remember which number it is.
Oh, no.
Six stop is the entry there. I think it might be a 17. Let's see.
Oh man.
Okay, exec. So terminal's gonna be gone. Kill all dash 17. That's my guess. A dot out. Okay, that's gone.
It did a thing.
So
Still got no
that
processes.
doesn't help. Yeah, and it probably would if it worked, unless it just took it a while. So I was hoping that maybe like we'd end up with one space. Like they're still all running, even if you do a kill all dash stop, they're just stopped. But if you stop them all, they still take up their entry spot. So then you just end up with a whole bunch of stopped ones. And I actually should have had a kill all out there working on this already. So I'm thinking that it didn't work. So if it's not 17, it might be 4.
I could look it up real fast.
Is that my last one?
I think it was.
Uh-oh. Oh, no. Oh,
Okay.
no.
I think we've killed the
Oh, I have
computer.
a few more.
Okay.
Yeah. Somebody wants to tell me what sig stop is. That's right.
That's 17.
It is 17?
It's 17.
Oh, bother.
Oh bother.
Oh.
Okay. Well, I think we're probably stuck here. I suspect we're going to have to restart this computer.
Congratulations. You
Okay.
just
I thought maybe
so-
debugging would be a good idea.
I was gonna say turned into Winnie the Pooh for a second there.
It'll be back up in a minute. So this is why you don't. Why I would like everybody to not practice these on iSoptra. Feel free to practice them on the machines in the room or your own equipment or whatever. The maximum harm from these things is that you have to restart the computer.
Yeah, Alex, don't practice them on iSoptra.
But
Put it in the audience.
this is one way that you can actually bring a software down with a regular user account. To the point I'd have to walk over to IT and push the power button because I can't even log into it.
That's kind of scary, actually, that it takes just something that simple can
Yeah.
just bork an entire server.
Yeah, yeah. Well, I didn't intend to lose control of it, but then when I did run the kill all demonstration, I lost my place I could push Control C. And
if someone were to do that exact set of things, it'd be problematic.
Oh yeah, yeah. Well, and you can also detach. So if you can have your very first one, go ahead and let the parent die, and that way you lose the handle to the terminal. That's how you make a game in a background process. You go ahead and call fork, you let the parent die, and the child continues. Anyway, let me back up in a few minutes. It used to be fairly reliable that you could stop them and get back, but ever since the multi-core craze, I'm not sure I've successfully managed to rescue one with the sig stop method.
Because there's just too many processes going all at once.
I guess.
Oh yeah, they're being exponentially created, so.
I kind of wonder if maybe it just doesn't manage to stop the ones that are actually active at that moment on the core or something like that, and a core, since there's 12 apparent ones. I don't know. Oh, hey, we can even restore our pages. Cool. Oh, hey, this came up. Okay. So that's a fork bomb, and so using exec, you can execute single commands. Oh, I wonder if my file does have anything out. Yes, output. Yeah, it does.
It has a lot of things.
Oh.
Wow.
Yeah. I don't think this is the complete table there. There's only 612 things in it. I think you can have more. For some reason, it it worked for a while, but didn't actually fill out the whole table. Okay. So that's what a fork bomb does. So if you're looking for some way to bring down somebody else's computer with only a user account, that's a pretty decent method. If you're the administrator and you're really concerned about these things, one thing you can do is limit the number of processes a user is allowed to start. There's resource limits available, so for anybody who's in Saudi and is like, but wait a minute, I'm going to manage servers someday. I don't want people fork bombing them. Yeah, you can limit it like that. You just say the maximum number of processes per user is like 800 or something like that. And then you can start whatever you like when you're trying to get rid of the fork bomb. And so then your stop process might actually work and you might be able to stop it. It also means that system services continue to function during a fork bomb, which can be quite convenient. Your web server, for example, will continue to stay up while the machine's fork bombed if you got this per user limit. Anyway, the per user limits aren't the default because users are sort of expected not to fork bomb machines. Okay, I don't have a whole lot more to say about fork bombs, but now you know. They're just an interesting curiosity of forks. Okay, so that kind of ends the process management stuff. When we're deeper into the kernel programming, I've always wanted to come back and either do as a class demo or as a project, have somebody make a kernel module that prevents the running of solitaire on the machine by looking through the kernel's table of processes and not allowing that one to continue. It was in there, like a kernel level time waster prevention. So I'd have to bring in my favorite solitaire program. And my favorite solitaire program, the reason it's my favorite, is it can play itself. Because normally playing solitaire is kind of tedious. You have to drag all the little cards around and process all the rules yourself. And so if your goal is to, say, win 10 games of solitaire before you start productivity for the day, it's quite an advantage if your solitaire program can play itself until it wins 10 times. In fact, you don't even have to watch it. You know, it could just like tell you when it's done. It's part of one of the games packages on Linux. I've actually kind of forgotten the name because I haven't played it in a long time.
That sounds like it defeats the purpose of solitaire.
What is the purpose?
To waste time. So now it's wasting time for you so that you don't waste time.
Well, if you really want to waste time, you can like win 100 games, and then you can play some other game while you wait for solitaire to win 100.
Exactly.
I mean, I guess.
Yeah, but anyway, so what I want to talk about today, just to keep us on track here, is system calls. And so system calls are one of many ways, a user process can request action by the kernel. Now, that said, a lot of the other ways that the user process can request the kernel do something end up involving a system call at some point. Like the files of /proc, where the kernel's attention is summoned actually via a system call, read or write generally, and then at that point you get some function to run inside the kernel, and it can do stuff on your behalf. So the kernel is very much, it has like grand priority over everything. It can determine what goes on, but yet it acts when the user space program calls it via system call. It's a really good example of servant leadership. Anyway, so the proc files in there end up calling read. So system calls have return and they have parameters with them. So actually, in effect, they work an awful lot like a function, where you call a function inside the kernel. That said, there's a lot more going on with them. You can't just call it a function directly. So these are part of the Portable Operating Systems Interface X for the most part on Linux. And so if you look for one, if you man to read, you'll see the read. There's a C wrapper for it. That's what you see here actually with these parameters. But there's a corresponding system call. And so if you look down on notes, read and similar system calls. And it's got a limit there on number of bytes that they'll transfer at once. That's 2 terabytes. So actually that could start to be a limit at some point. Now that's per system call. So if you wanted to read a file that's 4 terabytes, all you have to do is call read twice. And the fact is, with large file reads, you'll typically run read in a loop. Make sure you keep reading until you've got everything you wanted anyway. Since read returns at most however much you said. And so if you're reading from an optical drive, for example, and it's slow, read won't wait until the entire thing has been read necessarily before it gives you back everything. Same thing as from a network socket. Everybody in who took networks in last semester got to play with that. And in fact, read actually returns whenever there's any kind of pause and stuff coming over the network. I'll just go ahead and read right away. There's a network call called receive, recv, that you can give it a parameter that tells it, okay, just keep waiting until you've got everything I asked for. But regular read doesn't have that parameter. Okay, so anyway, if you're reading a large file, you probably have it called in some kind of loop until you've got everything you want anyway. And so it probably isn't something you'll notice, but it's down here in notes. That's why it's a note and not a bug. It doesn't really affect things too much. An NFS file system is a network file system. I would sort of like at some point in here, if we had a NFS file system that gave us unified files on all the computers in here, at least on the Linux side. I don't know anything about Windows side. I hear Windows 10 profiles are a hassle, so I don't even know Windows 10 profiles anyway. But on the Linux side, if we had a unified file system between each of them, then you wouldn't have to worry quite so much about sitting down to the right one. And then if we implemented some token protection of resources by having user accounts on these, it would help things. I say token protection because with NFS in particular, if you have admin access, you can read all of the files. And if you are able to install kernel modules on these systems, then it means that you have admin access. And so it doesn't actually protect things. It's like the privacy lock on the porta potty. It's not like a safe. Anyway. When I was an undergraduate, we had that set up, and so it's just known if you have something that you actually want to keep secret, then you don't keep it there. Okay. Oh yeah, but that's all on the side that I got into because I saw the name NFS right here, network file system. Okay, so anyway, you have a read system call, and there's quite a number of other things on here in the C also that are also system calls. For example, LCSC. And so LCSC repositions read-write file offset. And so it takes an FD, a file descriptor, and an offset that is how far off you want to be from where you started. And this is probably 64-bit. And you have this wince. And so wince is, well, I'd say it's an archaic word, but I'm sure Dungeons and Dragons people, for example, must use it. From whence are these orcs coming, Hard to generate an example on the fly since we don't use it all the time, but it basically means, from where. And so the from where is like, where is your offset from? And so you can have your offset from the end of the file or the beginning or the current position or whatnot. You got a few settings you can use for whence. Anyway, so that's LC. Now this whole off T. You got an off T in here, and I don't know if it has off T mentioned in here, what an off T is. Apparently not. But if we look at LLC, we can find something interesting. The LLC function repositions the offset of the open file. Okay, whatnot. But this function is Linux specific and should not be used in programs intended to be portable. And it has a note here, glibc doesn't provide a wrapper for that, so you can invoke it directly using syscall if you want. But you should probably just use LC. And in here it's got some notes somewhere about why it exists. Maybe not on this one. There it is. Exists on various 32-bit platforms to support seeking to large file offsets. Basically, it takes a 64-bit offset, and in the waning days of 32-bit, we could have a file that was over 4 gigabytes fairly easily. It's pretty common. It fit on the hard drives, but the offset type was still 32 bits. And so if we wanted to talk about being 47 gigabytes into a ripped Blu-ray on a 32-bit platform, it could actually be hard to do with regular LCSC. Anyway, so this is an example of a non-standard Linux-specific addition that's made to the set of system calls you can have, and these happen occasionally. And again, it's fairly clear to mention that you should probably avoid it if you can. Certainly you should, because if you can have your program compile and run perfectly fine on a Mac, you should. Even if you don't have one. It's good practice. Stay as portable as you can. Okay. So a number of people are probably out there thinking, but I don't like Apple products, so I'm going to make my program not support them. No, you can do that, but it attracts ill will towards you.
Well, maybe they should stop using that.
Right. I know Mac users are normally quite pleasant people, but the thing about Mac users is they're always in the coffee shop. I mean, that's where they are, right? And so they might throw their latte at you.
Or, this and accidentally throw it at their Mac.
Free caffeination.
Sorry, I very much respect Mac users, and I work with many of them. So I have to make fun of them occasionally.
It's not nice to tell me without me.
They all figure that I like being in a dark windowless office with all my text on my monitor. There was one time when Nina was over and in my living room, and so my computer was, I have a computer in my living room, but both my wife and I use it. And the funny thing is, it has a widescreen monitor. It was divided exactly 50-50 because the window manager tiles it that way. On one side we had Facebook, and the other side I've been doing something or other in a terminal, and I'm still sitting there. She's like, oh, that must be the computer you guys share. Like straight down the middle.
Masking tape.
Oh, that's bad.
Anyway, okay, but back to the point. Positive compatibility used to be available on Windows. It probably still is if you get the right library function. So, what point did I have there?
I don't know.
I don't even remember. I pulled these notes in and I skimmed them to make sure they still made sense, and now it doesn't make sense to me anymore. I probably said on some other philosophical, irrelevant thing today that makes up for it. Okay. So on Unix systems, generally returning a 0 means a success with some exceptions. So malloc and read, for example, are both exceptions to this. On a function, it doesn't really have any straightforward return value. The return value is usually the error, assuming it didn't work. And on other ones like read normally returns how much stuff you actually read. Malloc returns a pointer to something. So some of these ones return a value normally, and so then the 0 means that they didn't work. So can't put this as a totally. Just remember that most of the functions return a 0 if they worked, and maybe like a quarter to a fifth of them do the exact opposite. Okay. You need two pieces to make a system call. You got a user space library function, and then you got a kernel implementation of it. So let's play with read for a minute. Okay. So this will call read. So read is in unit.std.h. Okay. So we'll have main, and there's main, and so we want to call read. Okay. So we'll call read, and then we'll call write. So here's something read can do. Read can read from a file descriptor, and file descriptor 0 is standard input, and standard input is your keyboard. So let's go ahead and make a buffer, and I'll just make a static character array in, that's static, I keep saying static. It is static in effect because it's in main, and so it persists for the entire lifetime of the program. But we didn't say static. The fact is it wouldn't change a single thing in here if we wrote static, because that's how ones operate in main. But I keep saying that we're static for them, and nobody ever actually uses that or writes static right there. Okay, anyway, we'll just allocate buffer there on the stack instead of doing it on the heap or something like that. And we'll go ahead and say read. So if you look at the parameters for read, read takes a file descriptor to read from, so 0 is standard input. It takes a buffer to place everything, which is passed in as a void star. It doesn't know what you want to read. You could have a file full of integers that were stored in, just in binary as 4 bytes each, and it's perfectly happy with that. It'll read it into whatever you like, and then count, which is just how many 1-byte values do you want to read. Okay, so we're going to read from the keyboard, and we're going to read into this buffer, and we'll go ahead and say that, hey, let's read up to 100. Sure. Okay, so we should have 100 things in that buffer. I don't want to do 1024 in case it doesn't end up cutting off and I have to write 1024 characters of some silly story about giraffes.
I thought you liked doing that.
Yeah.
Then we'll go ahead and write, and we'll write file descriptor 1, and we'll write from the buffer, and we'll write how much stuff is in the buffer. Okay, so that's the length of the buffer.
I
So
feel like
this is
we've
like
gone.
the parent program.
I feel like we've gone back to networking.
Okay. So now it's waiting for us. There was once a giraffe that enjoyed eating thistles. Okay. Hey, cool. All I have to do is press enter and I can stop writing my story. So then it comes right back and it prints it out. So it reads in, writes out. So it actually calls 2 system calls to make this whole thing happen. So let's take a look at this program on the inside. Okay, I mean GDB. No symbol table loaded. I thought I just loaded it right there. Go ahead and build it with that G. And I should have done that to start with. Okay, just for the sake of the video and people in front here. All right, back. Okay, so now everything disassembles fine. What we've done in our program here in this x86 assembly, there's a few things that stick out as a call. And so we called read, and we called strlen, and we called write. And so the address of main here, which might be interesting if you've been looking at lab 3, which I forgot to talk about, and I'll try to talk about that at the end. These are all pretty close to the address of main. The address of main is right here. It's 400626. And so they're all 400 followed by 3 digits in the code segment. So these things are all in the code segment of our own program. And so let's take a look at what happens in one of those. So if we read, we can disassemble what exactly was meant by read. You can see we're in the right spot because we're calling the function that's at 400500. And here we start with line 400500. And we jump to somewhere and push something on and jump to somewhere else. 4004C0. And off we go there. Okay. We might need to go recompile this thing in a static sense, and so that's probably what we ought to do next. So normally when you link something, it gets linked in a dynamic sense. So let's go ahead and strlen. Okay, so if you look at strlen, we're doing basically the same thing. We're jumping to this spot 4004C0. We're pushing something different onto the stack, but then, off we go to the same spot. And you look at this and say, wait a minute, how can they even be the same? Well, we're jumping to an object that we're dynamically linked to that exists once for all the programs that use it, and therefore sharing all the code between these functions. So the way to stop doing that. So first of all, I'm going to go ahead and print out the size of our binary there. It's 12K. And then we'll go ahead and build it again with dash static. Okay. And then we'll look at the size. It has grown. So the reason it grew is when we said dash static, instead of using dynamic linking, it's actually pulled everything it needs into our binary. So if we want to use strlen, we get the whole code for strlen put into our binary. The advantage here, the reason that it has an option like this, besides what we're about to do, which is actually be able to look at the contents of these functions, is that you don't have to worry about what's on the system. So this is increasingly becoming irrelevant. If you remember Windows 98 and hunting for the appropriate DLL after you've installed some program and it's replaced one of your DLL files with an inappropriate version, static linking can prevent that. Because the DLL, Dynamic Link Library, is intended to be shared between different programs. And so the problem that people have on Windows 98 was that sometimes when you install a program, it would replace a system dynamic link library with an updated version that had additional functionality for the program that you just installed. So program A installs its special version of a system DLL, and then you install program B, and it replaces that DLL with its special version of that DLL. Then it might be that program A ceases to work. Had that happen? Yeah, it was very frustrating. Thankfully, things have gotten much better on that front. The usual way to make things better is to just say our system DLLs are not going to be replaceable by random programs you install. If they need to add functionality, then they need to encapsulate that functionality themselves, not change the system to do it. That normally works. There were an awful lot of things back then that required system changes in order to work right. Anyway, so GDB out this main, and you can see main is unchanged, except that all the addresses here for these things are different. Read is now located right there. Okay, now we've got something. This is the actual read function. Now, the read function is pretty short. The fact is, the main thing the read call does is make a system call. Now, it might do it in two different ways depending on how things are done. Now, maybe you might look at this and be like, why does it have to do syscall twice? I mean, surely you can't have to do system call twice. It doesn't. Start by making a comparison, and then you jump based on the results of that comparison to this line 43 F1 FD. If you look at this 43, where is it? 431 FD. Anyway, it's after the first syscall, and there's a return right here. Oh, here it is, 4341 FD. So two options. Option number one, we jump down here and do our call. Option number two, we don't jump, and we just go ahead and do the system call like we do it right up there. Okay. So yeah, I realize that you probably all had CS250 and learned MIPS rather than x86, yeah, I think the jump and compare and stuff is the same there. But
It's pretty similar.
yeah, okay, very.
Yeah, they're not that much different.
I learned MIPS too, but I learned MIPS like more than 15 years ago. So I pretty much forgot it. Okay, so we actually make a jump there. Now, before that, we're careful to move a 0 into register EAX, and then we do our system call. Okay, let's go ahead and disos write, since we got that in here. Okay, so write, I mean, it looks like the spitting image of read here, right? I mean, this is, I keep saying, well, yeah, I mean, correct there. But anyway, so the main difference is we're careful to move a 1 into this register EAX before we call it. Then we do the syscall, and then we go. Now, the syscall instruction, if I'd showed you this 10 years ago, we wouldn't see syscall there. We'd see int and then 0x80 as the parameter, which executes interrupt. It's 80 in hex, it's 128 in decimal. But anyway, that's basically what syscall does. We've got a special instruction for it these days, and so might as well use it. It executes interrupt number 80, which stops the CPU from what it's doing. So that's the user space side of a system call. So that's what we do to call it in the program. Now, following things through on the other side of the world. So this is the end of our user space world. Once we do syscall, we've interrupted the operating system, and off it goes. Okay, so LCSC Linux source. We go for 4.9 since we're currently running on this thing, and we go to fs and read write.c. Okay. So, and look at that, my about the right spot. Not quite the right spot, because I don't want VFS read. We'll talk about VFS read in a minute. We want regular read. There it is, right there. Okay. So we've got this. So syscall define 3 is a macro. It's set up so it looks a lot like a function right here, and that is what the macro will do. It'll just set up our function special for us, so we're making a system call. And so the macro actually has a number of parameters in here, and some of them are even types. But since it's a macro, it's just going to do cut and paste kind of things with these parameters, and it's going to assemble our system call and actually register it in a table and a whole bunch of housekeeping. Okay. So read is implemented right under here. And what we do with read, we do some getting the position and whatnot, but mostly we call VFS read. And so read expects an unsigned int that's going to be called FD. That's what ends up happening inside this macro here. It's going to be a system call called read. Takes some parameters there. One of the parameters is an unsigned int that is named FD later in this function. And we're going to have a char underscore double underscore user star, that's the type, and it's going to be called buffer, and that's where we put the stuff. And you can recognize the read parameters in here. They're just put out funny, and the macro will take care of all that. Okay, So once we're in here, we eventually call VFS read, and we call that using our file. So this, we get a struct FD, which is a structure to describe our file, and VFS read calls that. Write is right down here, and it's you know, it's a twin of read. It just does the opposite thing, and so for the most part, they're the same. Okay, so this is VFS read. Up to the top here. Okay. So there's a VFS read right down here, and so VFS read checks some stuff to see if we can't read it or whatnot, and after that, it calls double underscore VFS read, and double underscore VFS read finally does what I want to show you up here. So this is checking, first of all, to see how we read the thing. So you remember the file operation structure that we keep talking about? That is the data type of the FOP member of this file struct. So the file struct has a file operations structure associated with that, and in file operations has this member called read. And so if that is something other than 0, remember it's a function pointer, and so if we set it to 0, it's not a valid pointer at all. So if it's not set to 0, we go ahead and call it, and give it these same parameters that we would see when we implement read. Now we might also have read iter, which works slightly differently. That we could have that one instead of read. And so if we're trying to read a file and we don't have any read file operation for that file, we check to see if it has a read iter operation. And that goes off down a little bit different path. But if we don't have either of those, then we get an e-inval, an error. Basically, our file operation structure doesn't have any way to read this file. That could happen if you had a file system, for example, that did not support reading files, which you might
That doesn't
think,
sound very useful.
no, it doesn't. I can't think of an example. But if you wanted to have a write-only file system, I suppose you could. And then you just wouldn't populate either the read nor the read iter members of the file operation struct, just set them both to 0. And in that case, whenever somebody tries to read a file, they'll get an e-inval. Can't think of an application.
Being a pain in the tail.
Yeah, here's one way I could do it. Suppose for the the assignment turn-ins on Isoptera, instead of using the web-based interface like we do, there's also a command turn-in on Isoptera where you can turn things in directly from Isoptera, but it uses the web-based interface. Like it actually just goes out and talks to the web server and turns it in a normal way. But suppose we were going to do this differently. One way to do it would be to make a file, say one file per user, and so when you want to turn something in, you write it to your file, and you can't read from your file, but when you write it from the file, then the kernel goes and puts it somewhere else to be found later. That's a really convoluted way to do it, though. I can't think of an application. But anyway, so that's read, and that's where read comes through. And so write comes through in a really similar way. It's just going to go ahead and call this. Okay, so as far as what the macro does, well, so we pretty well found both ends of this thing here. You can see where the call happens in user space and where it pops through. But there's a matching that has to happen here after this is done. So if we look in the x86 and Arch, so the exact way that these system calls happen is platform specific. If you're running this on Android, you'd be going down the ARM branch here, except that Android is separated from the mainstream Linux kernel right now, and so you'd be calling the ARM branch on the Android branch of the Linux kernel, as opposed to the regular ARM one right here. There's kind of an intent in the community to merge these things back together and just have one kernel again, and it might happen at some point. The reason that somebody would want to do that, so if the mainline kernel makes an improvement, it's got to be moved over to the other kernel. If the Android kernel makes an improvement that we want back in mainline, then it's got to get moved over there. You see how it's a hassle? And so it'd be better if they were brought back together. And that's kind of the intent. Okay, anyway, so from x86, I don't know if I bothered to say where it is. So we need system calls. Okay. Okay, so syscall is an entry, that's right, it's in there. Entry is the entry point into the kernel, which we have to go through if we're on here. We look at entry 64.s. There's some interesting stuff in there. Okay. Okay. That's the fast path forward. I kind of wanted the lookup, actually. This file is kind of long. What would it say here? It would say syscall, of course, but it says syscall all over this file. There, I think it's just under this. It's fast path and slow path business. Return syscalls. Go to the very top. Okay. Only used there once. That actually calls into a C file right there. There's a lookup. There it is. Syscall table. So we call this function syscall table after we've got our system call and ended up in this file. So after the so you notice what we're doing here. We're using the contents of RAX and an 8 as the parameters for this function we're about to call syscall table. And we're in the system call handler. If you set an infinite loop in this file right here, like, you know, after this move, you just have, say, a jump back up to here and infinite loop it, that would really bring the system to a halt. As soon as somebody did a system call. So anyway, at some point we're calling this file syscall table, and the parameter here we're giving it is RAX. Now, this call actually calls into a file that's written in from the old C, not assembly. So if we look into grep sys, what's it called? Syscall table. And everything in here, we'll find one in syscall 64.c right there. And okay. So the syscall, that's not quite the right one actually. Actually, I think it might be right there in common.c. Okay. Okay. So eventually we have this. This is actually a table of syscall table functions. No, it's not quite right either. That's after we finished it. Maybe we just need to go to the system call table, which is up here. And so it's a .tbl file, the actual table. Okay. Okay. So this is the table of system calls to look up. So the value that we had in register RAX is looked up in this table right here. And so you can see the top one is read, second one is write. So remember, before making a system call in user space, we were very careful to set register RAX to either 0 for read and 1 for write. That's the values in this table right here. So that's where we look up these tables and figure out what it's called, which is read. And at that point, it can be connected to the function that was specified with that macro right there. Their indices into this table right here. That's basically what that value is. So that's where things get picked up. We run into the assembly code there. We take out the value of register RAX. We look up which system call it was, and then we can go ahead and perform it. Now, on x86, the way functions are called is probably different than MIPS, actually. On MIPS, did you push the function parameters onto the stack and then call your function? Did you call functions?
I don't think so.
Okay.
No, we didn't.
That's fine. Let me briefly explain how functions are called on x86 in that case. Okay. We need our function here. This main. Okay. Okay. So if we look at main on here, we're calling a function right here. Let me say call q read. Now before we do that, we do a couple of moves that seem weirdly specific. For example, we move 0x64 into register EDX, and we move whatever was an RAX to register RSI, and we move a 0 into register EDI. And then for write down here, same kind of rigmarole. We're going to move a 1 into EDI. We're going to move RAX, whatever was in it, into RSI. We're going to do something there, and that's going to change what's in one of these other ones. Basically, this is loading our memory address into the right spot. With strlen, you can see we're doing the same load right here. 0x border 110 off the base pointer. That's the location that our string is ending up at. And putting that into RAX, and then we're putting that into RDI. I'm sure there's a very good reason for that, but I can't recall. That it goes into RAX, and then whatever was in RAX goes into RDI. Anyway, so then on the other side of things, in function read, all of these parameters are actually in the right spot. The optimizer has done a good job here and mostly just put everything where it needs to be. The way you call a function, before you call it, you put the parameters into the right spots in registers on the CPU. And there's an order here on the registers for x86. I think the first one goes into, well, we can tell from here, probably RDX or EDX. There's a convention here. You keep saying R and E, and I keep talking about them like they're the same thing. You know, I said that, look at what comes out of RAX, and here, I said it was the same thing, but it's going into EAX. EAX is the 32-bit name for register RAX, which is 64 bits. AX, just regular AX, is a name for it if it's only 16 bits. And you can still use all these names. So if you're only going to talk about 32 bits worth of the register, you can call it EAX. The fact is they could have called it AX there and been fine, so we're putting a 0 into it. 2 bytes would be plenty. But it's not any faster. So we're putting these values into registers ahead of time in order to get ready for our function call. And then when the function is called, the correct values will already be in the registers, so we can go ahead and start operating with them. If we look at strlen, we'll go ahead and quit looking at that early. So the XMMs are floating point registers. I forget what the XMMs are for. These are newer registers that I haven't used very much. But anyway, when we start strlen, it will again expect to see parameters in particular areas, and it needs them to be in particular other areas, which is why it starts off by doing moves and moving stuff around. Instantly, Jesse, Jug Guy, McDonald, he sent me a
Jug guy.
well, he used to carry around this giant jug attached to this duct tape strap,
Yeah.
and now he has like this big mug thing instead. And so people that are new probably don't understand that. Yeah, yeah. So I used to call him Jesse the Jug, and he was like, and one day he told me, "No, I'm not a Jesse the Jug. I'm a juggernaut." I'm like, okay. Anyway, so he sent me a link to somewhere where somebody has built a compiler for x86 that actually compiles only using the MOV instruction for everything.
Oh yeah, he posted that on the computer science thing.
Okay. Yeah, it makes really long binaries, but it works. Okay, so with the system call, it's really kind of the same as calling a function in that you set the registers, then you do your system call, and then later something looks at the registers to see what you meant. There's only got a certain number of registers, and so the reason this doesn't enforce a limit, with the x86-64, the first 6 parameters are passed in registers, and then if you got more parameters than that, it starts pushing them onto the stack instead, and they have to come out of memory. With the 32-bit era, the calling convention was that they all got pushed into memory regardless. We got a lot more registers with 64-bit, added registers R8 through R14. And having these extra registers enabled this passing mechanism where you just put things in registers, which is much faster because memory is really pretty slow compared to CPU time. And so I'm figuring MIPS probably passes things on the stack, but it sounds like you didn't write functions in MIPS anyway, so that's fine. Okay. If you find an old timer, you can ask them if it was fun calling functions in x86 assembly, and they can tell you yes or no, or either.
Or have a heart attack and their brains explode.
Okay, back to the system call mechanism here. So that's what happens. Some memory manipulations required, not a whole lot. System call number goes in EAX, interrupt 80 is triggered using syscall nowadays. And we end up in N364.S, where we have to look up the system call, and the appropriate kernel code ends up getting run. In a sense of the purposes for system calls, usually a system call has a specific and particular purpose. So I think we're still saying, well, over here, we're still hanging out next to the system call table. So if you look at these, you can see there's read, write, open, close, stat. That gives you back statistics on files, so you can find out how big it is and that kind of stuff when you've got to open. fstat and lstat. These are all different versions of stat. They all kind of do the same thing in different ways. Like fstat, I'm pretty sure you're required to have it open so you have a file descriptor. I don't think you need one for stat. So there's little differences there, but they all kind of do that sort of thing. You got pull, which usually checks on various things. You got lseek, which brings you to certain points in the file. You can say, I showed you lseek earlier today. There's the lseek system call, and so on and so forth. And so there's quite a lot of these things that do things. If you're a networking class, socket, connect, accept, send to, receive from, send message, receive message. There's all those. Shutdown doesn't come quite where I think it's in order, because after that we got find and listen, and shutdown isn't a very common networking command. There's a bunch of those. Hey, there's fork. We talked about fork. Clone. That clones your process. It's a little bit different than fork. Exit. We've used exit before, I think, during the fork stuff to get out of things. Kill. That's used to send signals between processes. Obviously, they think that the usual best signal here is kill. F control, file control. There's general file control functionality. It's a little more general. Okay, so if you read through this thing, this might be a good thing to do while you have lunch or something today. Read through this list, and if you see one you don't understand, like BRK, then you just go over here and not done that one, and BRK. And, oh, that changes data segment size. Okay. You can memorize these things too. If you memorize them, then you'll know something that even old Unix programmers do not know, because they won't have it memorized.
Who cares enough?
You'll find esoteric stuff that everybody's forgot about for a decade.
They probably forgot it for a reason.
The fact is, most of these ones aren't completely forgotten. There's somebody that maintains the system call inside the kernel, and there's somebody who maintains the user space library that accesses it. And then there's a lot of people that use the user space library being blissfully unaware that the call even exists. That's the great thing about abstraction. You don't necessarily, when you're programming, always have to be concerned about what exact system calls are available. So a number of them tend to be used by library functions. Like, if you think about read and write, usually you don't call, I guess in networking you call read and write directly. You call read and write directly sometimes. But a lot of times you might be tempted to use like cout or printf or something like that. And you're using the read or write system call, but you're not using it directly. And then you're one step further if you're in Python and you're using print, At some point read is being invoked.
Somewhere.
I don't tell my CS111 students about read. Right, I guess in that case it's print.
Maybe you should see if you can confuse them.
Maybe I should. I don't mind talking about stuff that goes over half of everybody's head and then the other half is elevated a bit. That's fine. I just try not to test on it on a test too much.
Yeah, then you get angry mobs.
Okay. So generally speaking, they got a particular purpose, like read, not like IOCTL. Okay. We'll go find its number. Okay. So IOCTL takes a variable number of parameters, and it takes a file descriptor, and it takes a request. So the IOCTL function manipulates the underlying device parameters of special files. In particular, many operating characteristics of special files, e.g. terminals, may be controlled with IOCTL requests. The argument FD must be an open file descriptor. Second argument is a device-dependent request code. The third argument is an untyped pointer to memory. It's traditionally charred argp from the days before VoidStar was valid C, and will be so named for this discussion. IOCTL request has encoded in it whether the argument is an in parameter or out parameter, and the size of the argument argp in bytes. Macros and defines used in specifying an IOCTL request are located in the file sys ioctl.h. On success, 0 is returned. Usually on success, 0 is returned. A few IOCTL requests use the return value as an output parameter and return a non-negative value on success. On error, -1 is returned. I guess even in these cases, an error node is set appropriately. Conforming to, no single standard. Arguments, returns, and semantics of IOCTL vary according to the device driver in question. The call is used as a catch-all for operations that don't cleanly fit the Unix stream IO model. See IOCTL list for a list of many of the known IOCTL calls. The IOCTL function call appeared in version 7 AT&T Unix. So
it's a deep, we don't know where to put this, so let's put it here.
yeah, so I mean, if you read to the man page, then you're like, okay, so what does IOCTL do? The answer is
A little bit of everything.
yeah, kind of. Well, yeah, whatever something else doesn't do, I guess. So that's the opposite of having a single defined purpose. Now, that said, occasionally a catch-all is needed. I mean, how many people here actually don't have a drawer or other storage fixture somewhere that collects things that don't belong in any other storage fixture? You know?
The almighty junk drawer.
Yeah, so IOCTL is really kind of the junk drawer of system calls. The book actually has a paragraph on it in the chapter saying basically that in other amusing ways. Okay, the book goes through the process of adding a system call. I'm not going to. It's a good demo. If you're looking for an additional practice problem I didn't state, add your own system call to Linux. It'll be a good one. It might take you a while, but it'll be a good one. Learn some stuff along the way. Usually these things aren't added. Usually we use stuff like proc and dev for interface, and then end up using read and write, which in a way is sort of sidestepping the nature of read and write is very small, defined single-purpose calls. To say now we're going to use read and write to trigger function calls inside functions in /proc. But that's how we use them, and they still do have that purpose. And the read delivers information in, and write pulls it back out, and so it's not all that bad. Okay, reason for not adding these. Like, why not just add system calls for everything? Don't use /proc, just add more system calls. They're actually pretty fast. They're pretty simple to add. The book demo isn't that long. And actually, our code that we looked at in readwrite.c wasn't really that lengthy either. The lengthy part in that was figuring out what to do with it once it came back. And it's a read operation for some file that, it could be on a file system, it could be in /proc, it could be in dev. It could be on a CD on a different file system. It has to sort all that stuff out. So all that's pretty good. Now they've got numbers that are part of the kernel interface. So we saw this file that's full of system call numbers, and so those are the official system calls. So if somebody's writing a program to run on Linux, that's the guaranteed ones. And so they've all got a C user interface to use them. Whether it's directly or if it's like printf and they're called from something, either way, there's user interface up there for them, and so all that's good. Now, if you decide to add one, which you can do, I mean, you can download the kernel source and add one, no problem. You can actually add them in a module if you really want to. That's fine too. But if you add one on an unofficial number and the number's later used, then you have a problem, because now your program will invoke a different system call. It wasn't the one you meant to invoke, since they're just done by number.
That could definitely make some interesting things happen.
Right. And so if you really do need one of these, you can add it. Just pick a high number, at the end of the table, somewhere around 300 and some right now. So just pick one that's like, 1,050. It'll take a long time before it's a problem.
We'll invoke system call 65,535.
Don't pick an amusing number. It's like a staple of any kind of literature, just to make sure.
I was just quoting FF and X.
Yeah, you probably want to pick one that's like, it doesn't mean.
Not FF, FS. There we go.
Okay.
4X.
There's that. You have to have some user space C code. There's not like a virtual file system interface for it. And so you probably have to start an assembly if you want to use it from the user space, because you have to go ahead and put the right thing in register RAX and then trigger a syscall by using the syscall instruction.
No, we're gonna put the wrong thing in it.
So they're a little bit architecture dependent in how they work, which it just means you're responsible for the architecture independent nature of it. So if you only solve this for one platform, your program may be tied to one type of processor. But type of processor is pretty broad. I mean, most people here have an x86 in their laptop, right? Usually every class though, I've got at least one person who's like, mine's got an ARM. It used to be somebody to hold up an ancient Mac with duct tape hanging off it and be like, mine has PowerPC. And actually before that, they hold up a shiny new one that was that way. I remember that era. So it does make you responsible for being processor independent if you care about that. And so that's why proc dev and sys exist. Sys is the newer interface here. I don't tend to talk about sys very much just because it's newer than me. And I mean newer than me, not in the sense that I've been born since they wrote it, but it was pretty recent. I don't know. Later than I learned this stuff anyway. That said, we should probably add a file in it. It'd be a good exercise for me to learn how to do it. There's those. Proc is thriving and healthy, and so is dev. So now we got 3 of them. The thing about this kind of thing is a lot of times everybody's like, oh, we need one shiny new standard to unify all previous standards. And then we got one
That'll
more.
never happen.
And that's unfortunately a little bit of what's happened with /sys. But it would be good to learn how to use it. Okay, I put a practice problem on here. I'm going to start putting these on here. Did anybody do the practice problems last time?
No, I haven't done them yet.
I think they missed.
Okay.
I did too. I just hadn't gotten to them yet.
Well, if anybody really wants to get an outstanding score on a test, I started to put practice problems at the end of the notes. And I started that on Tuesday, so it hasn't been very long. So if the weekend before the test you do all the practice problems, or do them again if you've been doing them along the way, then you'll probably do better.
I was just saying, you could
It just started, yeah.
if you knew how long it was going to run, you could technically just use a counter to do that.
A counter to do that. Do
If
what?
you're good. Oh, that's talking about practice problem.
Oh, the practice problems. Oh, yeah. I see what, oh, you keep numbering them? I could, you're right. They could actually be in order. I hadn't thought of it. Yeah.
There's a lot of ways you
yeah.
can fiddle
Anyway,
apart with
so
that to make it do things.
this wasn't my idea. This is a suggestion. I don't know if I should keep the suggester anonymous or not, because it does make extra work that some people might do. Self-de-anonymization is allowed, but I'm not going to do it.
I mean,
Okay.
heck, that really wouldn't be that difficult. You just have to have it switch the true. You'd have to just make I'm going to shut up because otherwise I'm going to explain how to do it. Just realized that.
Actually do it.
Yeah.
Oh, yeah. Yeah, it shouldn't be that hard. I almost did it, but I was like, nah, I don't have any computer I really want to test this on right now.
Don't want to break your main computer there again?
I could, if I forkball my office computer, I can get it back up and going. And normally I've had an Nobium, my previous D machine, purring away in the corner, but it's actually off right now. They didn't want to SSH to a different one. He said I have to go turn it off and then on again if I make a mistake. And most of the ones I could access were, I could figure out one in here, but I'd have to figure out a way onto this network, which, yeah. Anyway,
It's
totally
doable.
doable. Yeah. Oh yeah. I want to briefly mention. So I put up a lab 3 practice with C. That's not it. It's not it. It kind of is. It's really practice with signals though. I don't feel like that's very descriptive.
Yeah, that's kind of
vague.
Counting 670 is a better one. Okay, I'll try and remember to change the title. It does practice with C memory. I think I was thinking about C memory addresses maybe when I wrote it last year or something. I don't know. Anyway, that's not really what it is. So there's a program, segv.c. But in the class examples area, I tried to explain what it's all about inside the program. I did that today. Basically, it makes this bad assignment right here. I is a pointer to an integer, but it just so happens that instead of an integer, it actually points to main. And you can't go change main. So this actually generates a segmentation fault. Like you're trying to modify a segment you can't modify. And so the program will receive a sig seg v. And so the lab is to add a handler for sig seg v that makes it not crash, just politely apologize and quit. So you just have to, instead of a signal handler like the other one is project 2, and I think I just closed it. Oh yeah. No, it's like next Friday or something. I felt bad making something due on Monday. What's that? Okay, yeah, so it's like next Friday, so you got like 8 days or something like that, which apparently should be plenty. And then there's project 2, adding stuff to the kernel. And so I'll kind of review how to do this stuff a little bit more, maybe next time or the time after, something like that. But everybody kind of has the right information from like about a week ago, last Tuesday's class. So you can do it then, or you can do it, I'll come through and review it, probably next Tuesday, probably on Tuesday. So I'd recommend starting this one well in advance. The reason is, although it sounds pretty simple, all you have to do is combine together 2 examples from class, the one on the proc files and the one on the keyboard blinking. There's a lot of potential to have some weird problem where you're like, instead of making the keyboard lights blink, it actually makes the keyboard stop working completely, and then I have to try and restart the computer using the mouse. So that started it going.
As long as it doesn't make the computer explode.
It won't. There's the only example I can think of in the Linux kernel where somebody's made a mistake like that. For a while, there was an error in the CD-ROM driver that would brick CD-ROM drives. Only certain CD-ROM drives.
Oh, that's great.
Okay. Anyway, that's about it. I recognize I'm out of time. So have a nice weekend.